The last addition reaction that we're going to talk about is hydroboration oxidation. And this is a two-step reaction sequence that converts an alkene into an alcohol. What we see here is that hydroboration is the addition of borane to the alkene, and that forms an alkyl borane here. And then oxidation converts the carbon-boron bond of the alkyl borane to a carbon-oxygen bond. Here are some specific examples. I love to show examples where you can see this both with a straight chain alkene as well as a cyclic alkene. And we can see where both of these, of course, have the alcohol functional group now. Of course, I want to point out that these two are symmetric, and so we will talk about what to do when you have different carbons here. But right now, both of these carbons, of course, are the same. So let's talk about borane for just a moment. When we talk about borane, this is a reactive gas that exists mostly as a dimer, which is shown as B2H6. So one of the things that you have to recognize is B2H6 a lot of times is just a synonym for BH3. I'm not sure if I spelled synonym correctly or not. Let's pretend like I did. All right, so for BH3. So boron is a really strong Lewis acid that reacts with a Lewis base. And so for ease of handling in the laboratory, it's really common that it's complexed with tetrahydrofuran, THF, which is a common solvent. And so you end up with this as your reactive species. So without further ado, let's go on and look at the mechanism. Now we're just going to look at the mechanism for the boration first. And the first step of the hydroboration oxidation is the addition of the elements hydrogen and BH2 to the pi bond of the alkene. And that forms an intermediate alkyl boron. So when we look at this, if we start with our friendly alkene here, right, and we have here, we see that the first step here is a concerted addition of the hydrogen and the BH2 from the same side of the planar double bond. So when we look at this, these electrons come down here and attack that boron, and then these electrons go up here to also form a new bond. You end up with a transition state that looks like this. Now, this species is called, or it's said to be a four-centered transition state. Right, because we have those four atoms involved. Then the product here, right? I just showed you the transition state, but really this is a one step. Is right here, okay? Now, I want to point out this is a syn addition to the double bond. So it goes on the same side. And you have no carbocation. So no carbocation rearrangement. Now, because the alkyl boron formed by the reaction with one equivalent of alkene still ends up with two boron hydrogen bonds, it can continue to react with two more equivalents of the alkene to form a trialkyl boron. Now, we often draw hydroboration as if addition stopped after just one equivalent here, but instead all three boron hydrogen bonds actually react with three equivalents of the alkene to form this trialkyl borane. Now, you only really need one boron hydrogen bond for hydroboration, so many chemists use a commercially available dialkyl borane, and those, let's see, commercially available, let's say dialkyl borane, right, which have a generic formula right like that, instead of using BH3. A common example is this molecule here. It's 9-boro-bicyclo 3.3.1 nonane. That's also known as 9-BBN. And this a lot of times is used as a source of that boron hydrogen. So maybe the burning question in your heart is about regiochemistry of this. Because previously I said, hey, look, we're using carbons that are essentially the same. Well, what do you do when your carbons are different, right? So this is a CH2 and this would be a CH. Well, with an unsymmetrical alkene, the boron bonds to the less substituted carbon atom. Right? And so this regioselectivity really can be explained with a couple reasons, but one is steric factors, right? The larger boron atom bonds to the less sterically hindered more accessible carbon atom. Now, electronic factors can also explain this too. If the bond making and bond breaking are not symmetrical, the boron will bear a partial negative charge in the transition state, and the carbon bears a partial positive charge in the transition state. And since alkyl groups stabilize that positive charge, the more stable transition state has the positive charge on the more substituted carbon, and we have seen that tons and tons, right? So, but let's put some words to that. Since the alkyl group stabilizes the carbon with the partial positive, right? The more stable transition state has the partial positive on the more substituted carbon. Okay. So let's look at some examples with a partial negative and partial positive so that we can visualize that a little bit. When we look at this in our inductive effects here, we see that when we form this transition state, there's the boron with a partial negative charge. Here's the carbon with a partial positive charge. This is the more stable transition state because that CH3 donates electron density here to stabilize it. If, right, the boron was to add over here, right, and it's got a partial negative then on this side, then that partial positive would end up being over here without an alkyl group to stabilize it. And so that's what makes this transition state less stable than this transition state here. So two big things explain why we see this particular regiochemistry. One are steric effects, and then two are the electronic effects. Now, this is just the first part of a hydroboration oxidation reaction. We have not talked about oxidation yet. So we have oxidation that follows the hydroboration. Now, alkyl boranes react rapidly with water and actually spontaneously burn when they're exposed to air. So they are oxidized without isolation with hydrogen peroxide, which is H2O2, in a base, right? So a lot of times this is said as basic hydrogen peroxide. And then oxidation replaces this carbon-boron bond with the carbon-oxygen bond, and that forms the new OH group. And notice there's a retention of configuration here. Now, the overall result of this two-step synthesis is syn addition. So we're adding to the same side of the elements, hydrogen and oxygen, to a double bond in an anti-Markovnikovs. So let's look at a summary table, because who doesn't love a good summary, right? So here is a summary of the hydroboration oxidation of alkenes. The mechanism: the addition of hydrogen and BH2 occur in one step. No rearrangements can occur. The OH group bonds to the less substituted carbon atom. Syn addition occurs, and OH replaces the BH2 with retention of configuration. Now, this is used in synthesis, and so here is an example. Hydroboration oxidation is one step used in making the anti-malarial drug shown here. So we do find that this is used in synthetic techniques to form different medicines. Now, I want to talk for a second about synthesis. So suppose that we wanted to synthesize 1,2-dibromocyclohexane, and when we go into the stockroom, all we can find is cyclohexanol, and we need to make this. And so how do we go about doing it? Well, one of the ways to do this is to work backwards. When you work backwards, from the product to determine the starting material, right? That's called a retrosynthetic analysis. Okay. And so a lot of times we want to work in the forward direction. We want to say, okay, what do I need to make here to go here, right? And then a lot of times though we can work backwards and say, hey, look, what do I need to start with here that will eventually get me here? So when we work backwards, one of the things that we need to ask ourselves, right, is that's a vicinal dihalide. How are vicinal dihalides made, right? And so when we work backwards from the product, we're really asking, like, what type of reactions introduce the functional groups in this product, okay? So what type of reaction introduces the functional group? I should have left myself more space there. I apologize, because that's kind of cramped, right? And then when we work forward from the starting material, we ask, what type of reactions does the starting material undergo? Right? And so in this specific example, I would ask myself, what reactions can alcohols go through that we've learned so far, right? And so when we look at this, I can think, all right, what have I learned? If I think about going backwards, right? I know that I can come here and I can say, look, I have this guy here, and I have learned that I can make a vicinal dihalide using Br2 and an alkene, which is here. Then I ask myself, okay, I've got a starting material of an alcohol. Is there anything that I know, any reactions that we've covered where I can take an alcohol and turn it into an alkene here? And if we remember back to our elimination reactions, we know we can use a strong acid. Okay. This is a multi-step synthesis problem. Multi-step synthesis problems are very common in organic chemistry. You will see there are lots of different ways to work them. Some people work all the way backward. Some people work all the way forward. I personally really like this method of kind of halfway back and halfway forward. And a lot of times it's a lot of trial and error as you work through these. My suggestion is to really know your reactions well, because with these reactions that we're learning, you are going to continue to use them through your journey in Organic Chemistry 1 and Organic Chemistry 2. My suggestion is do not just learn them and then forget them. My other suggestion is to write these mechanisms over and over again, because I think that's the best way to learn them just personally. But there are a lot of different ways you can learn them. I've had students before, to try to keep track of all the reactions, make flashcards. I've had students before make reaction notebooks that were incredibly helpful, so that they could have those organized, particularly the notebooks, organized so when they looked at problems like this, all of their reactions were in one place. I also want to point out that at the end of your chapter, there is a chapter review, and it'll show you the key reactions. So for example, on page 428 of this chapter, there are key reactions. And so I've had students before who've gone through each chapter and just photocopied the page with the key reactions to help them when they're starting to work problems like this, these multi-step synthesis problems. If you have any questions or just want to talk about different methods to help learn the material, I am more than happy to help. Please feel free to ask in class or stop by my office.